A very good afternoon to everyone watching this discussion with us here today. And thank you for joining us on a panel discussion where we interview experts in the fields of digital manufacturing and cybersecurity. Before I begin, I would be remiss if I did not thank our sponsors, especially the National Science Foundation, without whom events like these wouldn't be possible. Uh, my name is Dr. Susheem Kanwar, and I'm a postdoctoral researcher here at the NYU Tandon School of Engineering. First, I would like to thank Mr. Joel Lawson, who works as a cybersecurity researcher at the Oak Ridge National Laboratory. Thank you, Joel, for taking time out of your busy schedule to meet with us today.
Mhm.
Could you give a brief introduction for yourself, if you don't mind,
Of course.
and the work that you do?
Of course. My name is Joel Dawson. I'm a cybersecurity researcher at Oak Ridge National Laboratory. I work in the Energy and Control System Security Group, which is part of the Cyber Resilience and Intelligence Division at Oak Ridge National Lab. I've been here since 2017. I came on as a postmaster's just after graduating, and I was hired on full-time in 2019. And to give you a broad overview of the work that I do, I mean, it's kind of, you can kind of group it under the umbrella of cyber physical system security. And within that remit, I have pursued all sorts of interesting projects here that generally have to do with an attacker messing with a system that is interacting with the physical world and all of the sorts of weird, wonderful, terrifying things that can happen within that domain. So yeah, that's my general background.
Interesting. So it seems you've worked on and put your hands on quite a different number of niche areas within this field. And how did you become interested in it and end up where you are right now?
Well, so I got my master's of science in computer science at the University of South Alabama. So I graduated in 2017. One of my professors there was Dr. Mark Yampolsky. So I come from that line of thinking. I will say, Susheem or dear listener, that if you find yourself bored during this presentation, you can blame Mark Yampolsky. So yeah, that was my first exposure to the world of additive manufacturing security. As you know, Dr. Yampolsky was one of the first people to get in on the ground floor of that field. And while I found it to be interesting, my thesis work was in something slightly different. I was looking at rootkit detection using side channel analysis. So I wasn't quite doing additive manufacturing security, but I was building up a set of experiences with using side channel data and using that to infer some sort of cyber event on a system. Whenever I came to ORNL, I continued to perform some of my thesis work, but I was kind of doing the early career researcher thing, which is you just say yes to everything. And ORNL is a big place. It's the largest office of science laboratory in DOE, so there's no shortage of opportunities to do interesting things. And I was exposed to, I mean, we're at ORNL, we're very much a proposal-driven place. So, you know, you are given a lot of leeway to sort of propose projects that you want to work on. So we have an internal funding program called the LDRD program, which is Laboratory Directed Research and Development. There was an opportunity for me to write a LDRD proposal for a specific initiative that was looking at cyber physical systems. I wrote the pre-proposal on something completely different. And in discussions afterwards with the folks on the committee, they said that, you know, we don't know how well your proposal will go, but we know you have this background in side channel analysis. How do you feel about sort of adjusting your proposal to look at that? And I said, well, why don't we look at additive manufacturing or automated manufacturing as a domain? And so I was fortunate enough to get that funded. And so that was sort of my entree into actually doing work in this field. So that project, that was a 2-year project. It came to be called the Pisces Project. And we were looking at using side channel analysis to detect notional attacks. Since then, while I was working on that, I also became involved in the Cymani project, which is this kind of multi-party DOE-funded organization. It's led by University of Texas at San Antonio, where we are working on a series of initiatives to improve the cybersecurity and energy efficiency posture of advanced manufacturing. It's very broad. So advanced manufacturing of all stripes throughout the United States, but additive being so reliant on automation, so reliant on connectivity and sensors, it's a natural fit. So I've been able to continue some of the work that I started in Pisces and start some new research threads within the remit of Cymani as well. So that's how I got involved with it. It started
Wow.
with, and it ended up here.
Yeah, amazing. And you got to do and learn a lot of things along the way,
Yes.
it seems. What would you say a typical day is like in your line of work, and how do you find the learning curve to be? Moreover, would you say it's the work that you do is more of a lone effort working on your area of research, or is it more team oriented where a bunch of people work on a particular project together? Like, if you could explain that dynamic a bit better.
Yeah, so that's a great question. And I would say that, a bit of advice that I got whenever I first came to the lab was, one of the most important things that for a researcher to do is figure out what your strengths are and what your weaknesses are, and the sorts of partnerships that you can form that will complement each team member's strengths and weaknesses. So, advanced manufacturing security is a deeply interdisciplinary field. So there's really very little constructive or useful work that I can do by myself. So yeah, you do get very comfortable working in teams. Now it depends on the mix of folks that are in the group. It depends on the project. Since the pandemic, there have been plenty of folks who are still who are wanting to contribute to this field, but are working remotely. Like one of our researchers is actually working remotely from Alaska right now. So it's a typical day for me is coming in and we're writing a lot of emails, we're attending a lot of meetings. We're also spending a lot of time designing experiments. Because for additive manufacturing or manufacturing in general, it's a high-dimensional project. So you're thinking about how to design a good experiment that conveys the results that you want. And we also spend quite a bit of time writing and editing manuscripts. Again, because it's not, because it's so interdisciplinary, you're assuming that your readership, that your audience is coming from a diversity of backgrounds. So, you may be publishing in an advanced manufacturing journal, but you assume that cybersecurity folks are going to be reading that as well. So how do you explain the basics of, say, material testing to a cybersecurity person? Or maybe you're publishing in cybersecurity, but maybe if someone with a control theory background is reading that. How do you explain the way that algorithms interact with an actuator to a control theorist? So yeah, it's a lot. We juggle a lot of well, we wear a lot of hats, I'll say.
Yeah,
But it's very interesting work.
for sure. And how did you find the learning curve to be when you first joined ORN ORNL?
Well, the learning curve is pretty steep.
Yeah.
I mean, really, when you come to any national lab, there's going to be, I mean, there's a great benefit, if anyone is listening to this as a student, there's a great benefit to internships, because internships will expose you to a real world challenge in a very controlled environment. Whenever you get hired on, then it's less controlled, or at least you have these kind of pressures on your time and your ability. Thankfully, I've benefited from some really wonderful mentors and coworkers here, so that is a real benefit of working at a national lab, is that you have folks who are used to the mentoring process and are willing and able to sort of walk you through that learning curve. So yeah, again, cyber physical system security is fundamentally interdisciplinary, and I can think of very few programs that will give you all of the background that you'll need, especially in emerging fields. So, it's of great benefit. I think a previous interviewee talked about a growth mindset. It's great to come in with this assumption that you're going to be learning, and that you're going to take the tools that you learned in your formal education, and you're going to apply them to this new knowledge that you're acquiring.
Got it. Got it. And you mentioned how some of your time is spent as writing manuscripts, and especially making it more understandable for people from different fields, especially. And of course, there is your own research, and you also write grants for getting the internal funding,
Right.
etc. So, in terms of your day-to-day work, how much would you say the division is? So, how much of the time is spent in doing the actual research? How much would be spent in perhaps editing manuscripts or writing grants, and the remaining time maybe discussing with colleagues or managing teams if you're the head of the research group, I suppose. So how does that work?
I would say it depends on what sort of funding you're trying to get. So here at ORNL, we have a number of internal funding projects. So there's LDRD, and then there's something called SEED. SEED has a rolling deadline. So if you're writing a SEED proposal, it can be at any time during the year. LDRD has a fixed kind of time window in which the request for proposals drops, and then people spend time writing first a pre-proposal and then a full proposal if that pre-proposal goes through. So right now we're actually in the middle of LDRD season. So right now, my division of time, I spend a lot of time working. I'm currently working on a proposal. So I would say 50 to 80% of my time is spent working on that proposal. When we're out of season, I spend a lot more time on research tasks. So designing experiments, building test beds, running experiments, collecting data, analyzing that data. So that typically falls, I would say we do the bulk of our kind of hands-on research work in the fall and the spring, because we're also a government lab. So we're cognizant of both of the fiscal calendar, which ends at the end of September. So typically in summer, we're trying to wrap things up a bit and kind of put our findings into reports or publications, or maybe we'll be releasing a data set. So a lot of that work tends to happen in summer or early fall. So yeah, it's a seasonal thing, I'd say.
Got it. And what would you say is the thing that you enjoy the most about the work that you do?
Oh man, I love working on new and interesting cybersecurity subfields. As computing becomes ever more embedded within our society, every problem suddenly becomes a cybersecurity problem, which I love. I love learning. I love researching things. So it gives me an excuse to just grab a couple textbooks, sit down in my office, and try to, get at least a beginner's level of knowledge on a really interesting topic. So yeah, I've had great fun working in manufacturing cybersecurity, power grid cybersecurity, quantum cybersecurity. Um, just thinking about, I have a computer system that I can do things on, and then I have some physical behavior that computer system affects. How can I do weird and potentially disturbing things in the physical world by tampering with the digital world? And that's a to me, it's just an endlessly rewarding source of research ideas and projects.
Wow. Sounds very fascinating, how you look at it.
Mm-hmm.
And definitely, I personally also love interdisciplinary work and learning about new things as well, new
Mm-hmm.
subfields. What would you say are some of your most important contributions in the area or in
Yeah.
your field of research?
So whenever I started, so I'm gonna stick to manufacturing cybersecurity here. Whenever I started on the Pisces project, one of the first things we did was look at the literature and see what the gaps were. At the time, one big gap was that there were plenty of demonstrations and proofs of concept of attacks, but the attacks were fairly fine or fairly coarse grained. So for instance, if I am using just fused deposition modeling, if I put a void in the middle of my geometry, that void is really going to stick out if I'm using a side channel detection system or even just visually. All a person has to do is look at the print as it's happening and says, I didn't put that void there. Why is that there? Um, that obviously you can build in the weakness that you want in sort of a simulated sabotage attack, but you're really lacking in the stealthiness area. So one of the things that we wanted to investigate was the balance between stealthiness and um, attack effectiveness for an attacker. So for the Pisces project, we took an enterprise grade system as a desktop system, but it was a composite system. It was enterprise grade, and we were very careful. So, firstly, we fully instrumented the system with current sensors, but then we were very careful about thinking, okay, I have these sensor modalities. And if I'm an attacker and I want to avoid detection as much as I possibly can, which parts of the system can I make small changes to that will minimize my chances of detection while at the same time giving me sufficient control over the system to induce the damage that I want? So instead of creating a giant void, um, which I know will be noisy, I'm going to look for something that will allow me to render the same sort of damage that a void would do, but minimize the exposure, minimize the sort of delta that you'd see in a trained model. Um, so broadly speaking, I would say that the contributions that I've done have centered around that issue about engineering and launching attacks, how those attacks show up, and then if an attacker, firstly, ask if an attacker can or can't detect that attack. If they can't, what can they do to improve their system to make it more likely that they'll detect the attack?
Mhm.
Um, if they can, how reliable is that detection? Is there too much noise? What is the accuracy of your model? What can you do to remediate noise in the signal that's coming through, and give the defender, the best and most informative telemetry that they can get? Um, with with Pisces, we ran our simulated attacks. We were specifically looking at we were inducing changes on the heat block. So as the polymer filament came out, we were varying the heat. We were varying the amount of heat on the heat block, and we're doing that by tampering with the essentially it was through G code. So we're tampering with the pulse width modulation.
Mhm.
by setting new temperature gradients during the print. We were also tampering with the z-axis. So we're trying to induce a kind of delamination effect in our little test bar. So the idea is that if you weaken the juncture between the layers, then that affects the flexural strength of a part. We learned a lot of really interesting things. One was so there's a couple of interesting things. I'm looking off the side because I want to reference some of my notes here. So we first ran our experiments to kind of to simulate our stealthy attacks, and what we found is was a number of things. Firstly, so we were able to devise a system that detected all of the attacks. The system was built around a probabilistic optimization model. So we're using something called Markov chain Monte Carlo optimization that worked really well because one of the things we were worried about was noise. So we were technically in a lab environment, but we were working with a commercial system, so that gave us realistic levels of operational noise. And that noise can throw off, if you don't remediate that, that can throw off your sensors, that can throw off your model, both in training or detection. So we were able to handle the noise very nicely. But one of the things we discovered is that empirically, and this sounds intuitive whenever you think about it, additive manufacturing devices are tightly coupled. So even if I'm an attacker, I'm making a change on one actuator, there's a high degree of likelihood that that change won't just present in that actuator. It's going to migrate to other actuators. So one of the things that really shocked us was that, you know, we instrumented the heat block. We made an attack on the heat block. We assumed that the strongest signal for the attack would present in the heat block channel. That's not actually what happened. Our strongest signals invariably came from the X and Y motors.
Wow.
That really shocked us. A couple reasons for this. For one, for our detection system, we're using the Hilbert transform to isolate the instantaneous phase. Hilbert transform works the best the cleaner your your oscillatory signal is. So, you know, we needed some sort of oscillatory signal. The stepper motors, the X and Y, gave us the cleanest signal with respect to frequency components. So in a sense, you could almost think of it as sort of like an impromptu physics experiment. A lot of physics experiments, you're comparing a measured signal with a well-behaved local oscillator. We kind of that local oscillator for free from the X and Y motors. So that was something that could inform the application of these monitoring systems to a real world device. Another thing that we wanted to deal with was feature selection. This was kind of our first year project of Pisces, was looking at feature selection. And one thing we learned is that you can take advantage of the fact that a 3D printer is an engineered system. So it's not like I have some, you know, completely unstructured data coming from some natural source. I'm actually measuring semi-structured data. And that structure comes from the fact that an engineer has designed certain linearities into the system so that the system is maximally controllable. If you think about how your actuators are controlled, you can identify those linearities and use that as sort of go-to features that you can then put into your model. And so we got quite a bit of success there. Let me move on to some of the stuff that I've done with Cymani. One of the things we really wanted to focus on, so I participated in a project where we were looking at how to make very, very fine-grained attacks on an automated milling device. And there were two really interesting results that came out of that. The first is one of the first examples I've seen in the literature of kind of of what I would call a canonical cyber physical system attack. where I'm injecting, where in our attack was we were essentially doing packet flooding of a control board on this automated milling machine. And we were doing it in such a way that the packets would land at a certain time between kind of position write commands on the control board. So you have these legitimate writes that were happening. And depending on the timing where that attack packet landed, you could vary the size of the effect that you had. And so you could actually have this current measurement where you see where the attack happens, where the legitimate write happens, and then you can correlate that with the size of the change in the milling head that you saw. Most attack demonstrations that you'll see in the literature are, you'll see the attack. You'll see a description of the attack. You'll see a description of a high-level description of the system itself. Run the experiments, collect the data, and then you'll do some sort of detection on it. But you rarely see the granularity, the attack at that level of granularity. Another really interesting thing that kind of scared me, but I thought it was a really cool result, was in the world of malware detection. We talk about this idea of semantics preserving transformations. So if I'm a malware developer and I have a piece of malware that I know has been collected by some antivirus vendor, and they've made a signature of it. That signature is based on, the bit composition of my executable. But what I can do is I can say, okay, I want my malware to do X, Y, and Z. My code doesn't have to be in the same configuration to do X, Y, and Z. I can permute my code such that it still does X, Y, and Z, but when I compile it, I get a completely different bit string for my executable. The thing here was that we compared the power signature of our low-level packet injection attacks and modifications to the G code, and we found that we could induce identical attack behavior in the motors, but produce very, very different signatures in current measurements on the motors themselves. So that is a serious wrinkle if you're trying to define a model for detecting attacks. I now have to think about not just what the motor itself is doing, but I also have to think about the different places where that behavior can be created, all the way from the designer working on their system, all the way down to low-level driver behaviors. So, and to sort of flip that around, another thing we've been working on, we presented on this, but we're still working on this. This is ongoing work. Is in many more expensive systems, so especially systems where you're dealing with material that's very, very finicky, like metal powder bed systems, you have really nice sensors that if I was coming at this from a cyber point of view, I could never talk someone into buying those sensors, but they're already building them into the system because, metal powder does not want to behave. And so you need these very, very high resolution, data rich sources of telemetry, not just to enable very sophisticated closed loop control, but also provide root cause analysis and fault diagnosis after the fact. I, as a cybersecurity person, would love to be able to use those data sets or those sensors, those data streams, and potentially those models to detect cyber events. But I don't know for certain that there's not some kind of cyber attack that will get around those models. Those models were not trained to detect cyber attacks. They're trained to detect faults, just traditional faults. And so one of the things we've been thinking about and working on is there a process by which I can run some experiments on an existing machine, simulate some very general cyber attack scenarios and test to see whether or not my quality control sensors can actually detect those attacks. So yeah, that's what we're working on now. I think
Yep.
those are the contributions I've been able to make.
Wow, that's a lot, and you've worked in a lot of different areas and different projects. And you said that you especially like to work on new and up and coming subfields of cybersecurity.
Mm-hmm.
So, do you feel that there is a need for new standards? And what role, if any, have you played in establishing those standards when it comes to working in those fields?
I think practically standards are very important. In part, and for a number of reasons. Partly they can codify best practices,
Mm,
and they also act as a sort of motivation for participants in a field uh, to adopt certain best practices.
mm,
So you're defining what the best practice is, and then you're providing a justification for folks who are maybe trying to put off implementing those best practices or wanting to, but
mm,
having a hard time justifying the expense to say
mm,
that this is the direction that our industry is going. Here's a document that says that. Um, so, I mean, in that sense, I think that standards are tremendously important. It's also a great way to distill um, a lot of academic and lab-based work, and even work in the field, even received wisdom in a field, to a set of steps that you can then hand off to a non-expert, because cybersecurity is a fairly esoteric discipline. I don't expect the people who are operating additive manufacturing machines to have a PhD
right.
or a college degree or anything like that. um, so there's a real emphasis on usability, on kind of common sense steps that you can take, and standards help encode that and disseminate that to users. So I believe Mark Yampolsky talked about the ASTM standard. I've been participating in that team. It's been a fascinating and illuminating and at times frustrating experience.
Mm,
There's quite a bit of adaptation that has to happen with kind
mm,
of you know, received standards and wisdom from classical cybersecurity, just traditional IT cybersecurity, adapting that to additive manufacturing. That's more challenging than it sounds. But
yeah.
yeah, we're actually getting near the end of having this advisory document, informational document that we can publish.
Wow, amazing. So looking forward to that. And with the advent of and increasing use of things like AI, LLMs, machine learning, all of that, how do you see the field shaping up, especially in the next 5 to 10 years?
So that is a great question. Um, I would love to say that I can predict the future, but I can't.
Oh, wow. That would
Uh,
be great, wouldn't
oh, it would be great. It would be very,
it?
very useful. Um, so, I will say that whatever predictions I have here are based on just a general, informed sense about what I think is going to happen. But there is a degree of speculation here.
Mhm,
Uh, so we were talking about standards. I do think that one way the field is going to shape up is that you're going to see more standards.
mhm,
I think we're moving that direction, and we've sort of beat the drum on cybersecurity in advanced manufacturing enough that we can justify writing these. So that will change the landscape a bit. Is that uh, you know it will be both an obligation and an opportunity for businesses and device vendors um, to utilize these standards in building security into their devices or their deployments. Um, One of the challenges I think of writing any standard for additive manufacturing is just how to deal with the heterogeneity of the field. So, you know, a security policy for a powder bed fusion system is going to be different than one for like an SLA system. It's going to be
Right.
different from one for like a hybrid, hybrid machining directed energy deposition system.
Right.
So any good standard is going to take advantage, is going to acknowledge that an attack against one technology is going to look different than an attack against another, and that if you want to build a proper policy from a standard, then you need to be able to perform some sort of assessment of your unique needs and then
Mm-hmm.
tailor your policy to that. One thing that I think will be really interesting is watching just the field itself develop. So right now, the kind of high-end additive manufacturing market is contracting a little bit because, and I think that this is a healthy thing, I think that the use cases for high-end systems are going to mature.
Mm.
People will get a better idea of how, dropping 500K on a, laser powder bed fusion system is going to help their business case. And by extension, the abuse cases are going to mature as well. So because the field is relatively new, if I'm an attacker, I can't, there's going to be there's not just heterogeneity of technologies, but there's heterogeneity of the way these systems are used. So I might, target a laser powder bed fusion system at business A, and I develop an attack for it. I don't know with any degree of certainty that attack is going to be applicable to a different business, because maybe business A is working in aerospace and business B is working in railroads or working in the power grid. An attack that's meaningful to business A is not necessarily going to be meaningful to business B, and so that makes my job a little harder.
Mm.
As the use cases mature, you as an attacker can assume that there's going to be more continuity between different kinds of businesses as best practices for using these devices mature as well. So,
Right.
it's I don't like to say this, but I do think that that the process of developing attacks will in some ways become easier for that reason. So Mark talked about, a public attack or potentially. So I think in the next 5 to 10 years, there is a potential that there will be a Black Energy 2 style attack. And Black Energy 2 was this malware that was used to attack the Ukrainian energy grid, I think back in, let's say 2014, but I might be wrong about that.
Mm.
Um, the Black Energy attack was a great sort of, it was intact, so it's not good, but it was this proof of concept. It was an example of what bad stuff can happen if you don't secure your power grid. And
Mhm.
that was a motivating example for the power industry in the US. Previously, you would say, so if you think about the incentives of power generation and distribution, because the profit margins are fairly slim, adhering to regulation and the fines that come from not adhering to regulation are a motivating factor for utilities over here.
Mhm.
So if if a regulator sees this example attack and says that, okay, we're going to update our regulations, utilities are going to sit up and take notice.
Mhm.
So in that sense, where before utilities, which were very, very focused on stability, and cybersecurity was seen as a potential source of instability, that they wanted to minimize, they wanted to minimize the application of cybersecurity to the grid because of the fear that something would break. Now, cybersecurity becomes a source of stability that they need to incorporate into their system, and so that was
Mhm.
a motivating factor for them. The reason I bring that up is that you know there's of course the possibility that there will be this sort of public attack, but the question is, what does that public attack look like? How does that feed into the sort of fundamental motivations of additive manufacturing? So if I'm a vendor and part of my competitiveness is based on my IP, and I have some flaw in my cybersecurity controls, and a foreign company is able to, take my IP, reproduce it, and undercut me and put me out of business, that's a very scary thing, and that's a motivating example
Right.
for vendors. If I'm a user, then maybe I'm really reliant on, I have these expensive machines, I want to have as much uptime as I possibly can, but if my availability for these machines goes from 90% at any given time to 40%, that's a very scary thing.
Mhm.
So I guess another thing I would like to throw out there is this idea of secure mechanical engineering.
Okay.
So we have this idea of secure software engineering. I
Right.
can I can build practices and processes into my software development uh, pipeline such that it can alert me to vulnerabilities. It can, in some cases, automatically fix them. In other cases, will just tell me that they're there. But at the end of the day, I I induce a very small expense at the beginning whenever I'm building the software for the first time versus having to kind of retrofit something that's already in production after the fact,
Mhm.
um, to respond to an attack or a new threat. I've been thinking about how you'd apply this sort of thought to the actual process of designing something that you're then going to print. Um, so if so one way to think about that is like, okay, I know that, I know there's this risk that an attacker can get into my system and make some sort of change to my tool path that would create this damaging effect.
Mhm.
But as we've established in the Pisces project and other experiments, um, the you know the ability to perform a damaging attack depends very much on the geometry itself. So I'm an attacker. I want things to be stealthy. I want to make a very small change, but I also want that change to give me the result that I want.
Mhm.
If I'm making some geometry and I run it through, a mechanical simulation where the stress points are. If the stress point is on a very, very small part of the model, I know that an attacker will most likely want to make that change if the attack is meant to induce some sort of mechanical failure. So you then ask yourself, okay, what are you going to do? I mean, maybe what you can do is you can look at your in situ monitoring system and say, I want you to expend extra resources on this region of the geometry. Or if you can do this, you could potentially just add extra material there.
Yeah.
Or you could, if you're using something like generative design or topology optimization, you may get multiple geometries that adhere to the specifications that you provided. Um, Maybe part of your selection will have a bias for, you know, minimizing stress on any given part of the geometry. So that's
Mhm.
what it's that's what I'm sort of tentatively calling secure mechanical engineering.
Yeah.
Um,
All right.
yeah.
And thank you for sharing that thought. And I guess we'll see if we've actually managed to predict the future
Right.
in the next 5 years.
Yeah.
Finally, what's one piece of advice you would love to give young professionals entering the field today?
Well, I would say for this particular field, prepare for interdisciplinary work. This is
Yeah.
I could say with a high degree of certainty that the field's going to change
Yeah.
over time as new technologies come out, as computing power uh, grows and becomes more distributed. So you know, prepare yourself for that. Also, just know that there's no 4-year degree or grad degree that is going to give you all of the expertise that you need.
Mhm.
So again, to go back to this notion of a growth mindset, this is a cyber physical systems in general is a great field if you love to learn. Also, prepare for the fact that you'll be on these multi-party teams. This is not really a field for lone geniuses because you know you are going to struggle to provide the level of insight that's necessary to get something useful. But also, if you're on one of these teams, you're on one of these teams for a reason. People are relying on you for your expertise in your field. So if I'm coming at this, if I'm part of a additive manufacturing security team, I'm bringing my computer science and cybersecurity background, and that is a true asset. Much like, a colleague will bring their material science background. That is an asset for me. I may have an idea, but I need to talk to the material scientist to bounce that idea off of them. And the value of that idea may depend on the deep expertise in material science that the person I'm asking has. So it's a negotiation. You'll do a lot of communication. You'll do a lot of kind of explaining the basics of your field to other folks, but that's not a bad thing. And at the end of the day, you'll have a valuable output, I think.
Yeah, well, sir. Thank you so much, Joe. Thank you so much for your time and for your insights. It was a lovely discussion. I'm sure our viewers will enjoy it as well. Thank you.
Thank you, Susheem. I appreciate it.